Everybody, and welcome to APS Webinars. The title of today's webinar is The Framework for the Next Generation of Science Standards. I'm Crystal Bailey, and I'll be your host for today's broadcast. Thank you so much for joining us. APS Webinars are brought to you as a service of the American Physical Society, connecting you with the expertise of individuals who can offer insight into physics careers, educational programs, and professional development for students, working physicists, and educators. Today's presentation features Helen Quinn and will be moderated by Noah Finkelstein. They will be discussing the framework for K-12 science education that is the basis of the coming next generation science standards. There's going to be some Q&A actually during the presentation today based on questions that came in when folks registered. But at the end of the presentation, we will still have the remainder of the program for a live Q&A session. Because of the number of people attending this webinar, we are only accepting text questions. So if you would like to ask a question, please type it in your questions panel located on the right side of your screen. You may ask a question at any time during the broadcast. We will do our very best to cover all the questions you submit at the end, but we do want to apologize if we're unable to cover everything. I think that Helen may actually be able to stay for a little while after the official end of the webinar also for a continued discussion. So if you want to stick around for that, we'll stay for a few extra minutes. Finally, a link to the recording of today's presentation will be emailed to you after today's event, so you should receive an email from GoToWebinars that will contain the link to the recording. Please give us 24 hours to upload the video to the site. And also, whenever you exit today, we do encourage you to complete the survey so that APS Webinars can improve its ability to provide you with valuable services like these. So with that, let's go ahead and get started. Noah Finkelstein is an associate professor of physics at the University of Colorado at Boulder and conducts research in physics education. In addition to serving as director of the Physics Education Research Group at UC Boulder, he has also served on a number of national boards in physics education and has served as a co-PI and director of NSF education initiatives relating to STEM learning. Noah has also won several teaching awards at the University of Colorado and was recognized as an APS Fellow in 2011 and as a Presidential Teaching Scholar for the University of Colorado System in 2012. And with that, Noah, I will turn things over to you.
Thanks so much, Crystal. It's a great pleasure to be here. I'm excited with the turnout and this webinar. We're very, very fortunate to have Dr. Helen Quinn join us. And this webinar, as Crystal mentioned, is dependent on you all who are participating. So please do send your questions. Many of you sent great questions in that we will incorporate into the presentation and address at the end. So we're very fortunate to have Dr. Quinn with us. She's a professor emerita of particle physics and astrophysics at SLAC National Accelerator Labs at Stanford University. She's a former president of the American Physical Society and is a member of the National Academy of Science. She's internationally recognized, of course, for her contributions to particle physics. And what brings her to us today is her long-standing involvement and engagement in K-12 science education throughout her career. She currently chairs the PhysTech Advisory Board and is chair of the National Research Council Board on Science Education. In fact, it was in that latter role that she chaired the study of the committee that developed the framework for K-12 science education. And this is what she's going to present to us today and is eager to take your questions that I will moderate. So let me turn it over to you, Helen. Thank you so much for joining us.
Okay, and welcome everybody. I'm going to hope that my slides will move as I click the right button. Yes. So I'm going to start with a little context, which probably everybody on this line knows, but the first issue is education is a state concern, and therefore there is really no national standards for anything. However, as you know, there's a movement towards states voluntarily joining together to have common standards, and that now has happened in math and language arts. And the next generation science standards are intended to be the same kind of thing for science. They're not being called Common Core Science for political reasons, but they're going to function very much like Common Core. The development of these standards is being done in two stages. The first being the framework, which I hope most of you have already looked at, and the second being the standards, which are being developed now, and there'll be a public release of a first draft in a week or so, I believe. So looking at the standards writing work, you see that there are 26 states involved with Achieve in that work, and that means there are teams that include teachers and educators of various levels from each state involved in reviewing drafts that are not the public drafts before, and between public drafts there are state team drafts that are being published by Achieve just for that group. So if you're in a state that is one of these states and you want to know more, talking to your state team is the way to find out more. It's also a process which is trying to help the states think about what to do to be better organized for when these standards are available and states start to decide whether or not to adopt them. Of course, a framework and standards is not what happens in the classroom. What happens in the classroom is teaching and learning based on the curriculum materials, the instruction that the teacher delivers, the preparation and experience that the teachers have, and the assessments that are being used to judge how students are progressing. And all of these elements have to change in alignment for any change in education to actually happen. And so the framework is just a very first step in a process of realigning all the pieces. And today we'll talk mostly about the teacher preparation piece, but I think this is to give you a context that we're well aware that framework and standards are only a small part of what needs to happen.
Helen, let me interrupt and pose a few questions that have already come in then so far about the construction of the framework and then the associated standards. And either you can answer them now or along the way. Is that all right?
That's fine, yes.
Super. So Dave Meltzer of Arizona State writes, how were the framework learning targets guided by research on student learning and corresponding grade levels? That is, to what extent was this driven by research? Trina Cannon from Highland Park in Dallas, Texas writes, when putting the committees together to generate this document, were high school teachers present, or if not, why not in this? And then finally, we just had a question come in from Jim Eakins asking how this might be drawing from No Child Left Behind or prior efforts of the Elementary and Secondary Education Act.
Okay, well, first of all, to the construction of the framework, everything that the National Research Council Board on Science Education does, we try as much as possible to base it on research. And that's actually the main role of the Board on Science Education, is to accumulate the accumulated knowledge of research and put out reports like Taking Science to School or Ready, Set, Science that are capturing that research and saying, what does it tell us for the classroom? For the framework, we did that, but of course, in order to do the full job, there are areas where we had to make our guesses, best guesses of the committee, based on the areas where there are research. Because if you look across the topics, some of the topics like understanding matter have a fair bit of research on how they develop across the grades, and others, such as understanding climate change, have a lot less of that research, although there is some even on topics like that. So where there was research, we tried to use it to guide how we developed, and then we tried to make some kind of uniformity across all topics of what we did at what grade levels. And so it was definitely as research-based as we could make it. Then as to who was on the framework committee, the committee was 18 people. I dropped that slide out of this presentation. 9 of them were members of the National Academy, scientists, including a couple of Nobel Prize winners. The other 9 were people with a background in science education. That included a mix of people, none of them actually teachers right now, although many of them had been classroom teachers earlier in their careers. So people like Brett Molding, who was state science supervisor in Utah. Actually, Stephen Pruitt, who's the head of Achieve, was on the committee until he got a new job at Achieve and had to drop off the committee. And Deb Smith, who used to be a kindergarten teacher and now is a teacher educator at Penn State. So a range of people who've done research on science learning and people who've done research on assessment of science learning. So we had quite a mix on the committee, but very few actual classroom teachers, partly because of the time demands of being on the framework, and partly because we felt the role of teachers in writing the standards would be much more important than in looking at the big picture, which is what the framework does. What is the most important thing? What are the most important things for students to learn? We weren't getting down to the level of what details they should learn in which classes. That's much more an issue of curriculum. And a lot of the time in the framework committee was carefully saying, we're not writing curriculum, we're only writing at the top level, what should students be learning? And there's a lot of work between a framework and a curriculum that exemplifies that framework. As to the last question, you're going to have to remind me. 3 questions.
Right, this is
too
about...
much for my poor brain.
No. This was about how is this designed to respond to sort of national policy, No Child Left Behind or other...
So No Child Left Behind is, of course, focused most on reading and math. A few states assess science. So the question of how science standards fold into state-level assessments is very different state by state, and more states are beginning to give science more weight. The issue here was not so much about assessing schools and teachers, but about making sure that people understand that science is important for all students to learn, starting in kindergarten. And we felt if we didn't have a set of science standards that made that clear, we didn't even have the first step in ensuring that all students have access to science learning. How that access gets translated into requirements and evaluations of schools and teachers, that's quite another set of things and not addressed at all in the framework.
Wonderful, thank you.
Okay.
Well, let's turn to the framework itself.
Let's go on, yes. All right, I guess I somehow have to click on my screen again. Oh, I know. I have a dead keyboard and I've got a separate one and I'm clicking on the wrong keyboard. The way the framework chooses to describe science is as having 3 dimensions, and I'm here just telling you the 3 dimensions. We'll get into them in a lot more detail as we go through this. The first dimension is the practice of science and engineering in this case, because we included a little bit of engineering, both because we think applying science in engineering design activity is a way to learn science, and because we think every student does need to know something about engineering. And if it weren't in science, particularly K-8, where would it be? At the high school level, everything we've done is organized in a different way from high school courses, and figuring out how the pieces of this framework fit into the course structure is a challenge for each school and each state to think about. Second, cross-cutting concepts. These are ideas that cut across all disciplines of science and are often not taught because they're kind of in the background. We think they need to be foregrounded a little more, and we'll come to what they are and why as we go along. And then, of course, what people usually think of as the content, which is the disciplinary core ideas of the subjects. What we're saying is the practices are just as much content as are the core ideas, and the cross-cutting concepts are also important content that all students should learn. And so we're expressing this, it's 3 dimensions, with the idea that a science lesson should be 3-dimensional. Of course, this, even just at this level, you can see that this raises some challenges for teachers. For example, if you want teachers teaching science practice, well, one would hope they've had some experience of science practice. And where do they learn about the cross-cutting ideas and how to think about and present and interpret the cross-cutting ideas at the right level for their grades, it's not obvious in the current system where these things are learned. I think high school teachers perhaps have less problem in interpreting those things, although, again, many of them will have not actually engaged in some of the practices. But at the high school level, there are also challenges. If you think about this way of talking about cross-cutting ideas, how do you make sure those cross-cutting ideas get expressed in a similar way across all courses? And how do you incorporate all of the knowledge that every student should have into some sequence of courses? And what does that mean about teacher preparation? So these questions I don't have answers to. I'm just saying they're challenges, and we will talk about them more after I've talked more about the framework. So the goal of the framework is that students should, rather than learning a bunch of disconnected things in disconnected courses, really develop an understanding of certain core ideas of science across multiple years of school. And secondly, that they should experience a more seamless blending of science practice with science core ideas and cross-cutting concepts. So here's the list of practices. The ones highlighted in red are ones that, if you talk about science inquiry, often get left out. When people talk about inquiry teaching, everybody's clear that that involves planning and carrying out investigations. Unfortunately, and again I'm talking both at the elementary and the high school level, so some of the things I say may not apply so strongly at the high school level, the step of going beyond collecting the data and going to analyzing and interpreting the data is often underemphasized. Similarly, the step of arguing from the evidence, asking does this evidence support or not support the explanation and the prediction based on that explanation that I thought applied to this system. Number two, developing and using models is one I stress a lot. If you're a high school physics teacher who takes a model-based approach, you're very well aware of this. However, if you're a biology teacher or a elementary, say, second grade teacher, being aware of this as a core science practice and having students be very explicit, every kid, whatever they're thinking about, they have some kind of mental model, and making them make their mental model explicit in diagrams and words and discussion helps them clarify their thinking. And understanding how to have students do that and use models throughout their science learning is one of the new stresses here, which I think can be very powerful, but it requires teachers understanding how to do it. I'm going to stop and let Noah ask any questions he wants about this. I'm flying through this to give you plenty of time to talk and ask questions. So, Noah, are there questions about the practices?
Yeah, there are three classes of questions about practices here. One about teachers, another about assessment of these practices, and another about undergraduate level. So maybe we'll take these sort of piece by piece. And why don't we start with the teachers and the implications for teachers? This is, in some sense, what breaks out in terms of outcomes, as you suggested, from the framework and then the standards breaking into these areas. But
yes. So let me start with the actually slightly tilting toward the assessment side, because I think it's important that people recognize that the standards which achievers writing will involve performance expectations that include practice along with core ideas. So evaluating these practices is definitely going to be part of what the standards ask for. Now that means
and so does Dave Pritchard. He wants to know how is this going to be measured.
Well, that is a real challenge, and we're going to need to do some work on how this is going to be measured, and I'm hoping to get various people active and investing in supporting that work, because I don't think a multiple choice question that asks you to label the parts of a diagram or apply a formula in a standard way gets at these practices. And so this is placing not only a demand on the classroom, it's placing a demand on assessment. At this point, I always like to say this framework is a recipe for evolution, not revolution. All of these things need to happen, but they don't need to happen tomorrow. And that means it's going to take time before we get everything aligned, but I completely understand the bind that teachers are in if their assessments are asking for one thing and their standards are asking for a different thing. And I think this is one of the challenges of trying to achieve change. But I think when you show this list of practices to scientists, they nod their heads. So this is what scientists do, and I think it's extremely important that it is therefore what students do as they learn science, both in order to support the learning and in order to understand the nature of science and what science is and how a scientifically derived piece of information is different from an opinion.
Wonderful. Thank you, Helen. And a question comes in, and I'm pleased to have heard your answer earlier, but Heather Sinclair asks, who will be developing, adopting these assessments for these frameworks? Are you at liberty to share the movement going forward on this?
That's not yet really defined. The one thing I can say is there is going to be a National Academy Board on Testing and Assessment and Board on Science Education panel working over the next year or so, developing what's called a framework for the assessments of this framework. In other words, asking exactly the questions you're asking. What does it take to assess these kinds of things, and how should that be done, and recommending what work needs to be done in order for that to happen right. So at least some funders have thought it was worthwhile to do that piece of work. I think one of the challenges in this current time of making educational change is finding the funding to support all the work that needs to be done. And I am not naive enough to think this can happen just by magic. So clearly there's investments to be made. I think that study is a good step in sort of framing and directing those investments. I hope that then NSF, for example, might step up to funding some of the work that needs to be done, and maybe some foundations will also think this is worth their while, because it is a very important element of implementing a new view of what science learning should be. And by the way, when I say new view, I know there is nothing in this framework that hasn't happened in some classroom somewhere. In fact, hasn't happened in many classrooms. The new view is simply putting it together in this particular way and saying all of this should be happening in all of the classrooms.
Thank you so much
Did I
for that.
capture all those questions now?
Yes, and in fact, there's appreciation for that going on online, which is nice. And thank you, everybody, for your comments and questions here.
So let's move
and we'll
to
come back to teachers and undergraduates later on.
Yes.
So those will come back.
Okay, patterns, cause and effect, scale, proportion, and quantity. These are not new ideas. Patterns, of course, because noticing patterns is the beginning of a way we ask questions in science, and trying to interpret them in terms of cause and effect is partly the way we think about science. Cause and effect, for example, is very interesting. Almost all of science is about cause and effect mechanisms and explanations, and yet you very seldom hear that term in science classrooms. It's in the background of the scientist's mind, but not in the foreground. And what we're saying is it should be explicit and just repeated over and over again, where we're trying to look for mechanisms and explain cause and effect in this system, which takes me to number 4, systems and system models. At every level, starting in kindergarten. You can talk about what is the system we're looking at here, what are the parts of the system, how do those parts interact with one another, what are the boundaries, what's flowing across those boundaries. There are sets of standard questions that can be asked over and over again throughout a student's science learning that then become habits of mind that the students apply when thinking about science in the next context they meet. And that's the idea of these cross-cutting concepts. They should be so automatic and so repetitive in the sense of the way they're used that they become second nature to the students to think about and ask questions about these things as they examine a particular system to try and understand a particular phenomenon. So that's the idea of these cross-cutting concepts. Let me talk a little bit about energy and matter. Now, notice, first of all, that energy conservation is here put as a cross-cutting concept rather than as a core idea under physics. Energy and the details about energy that you learn in the physical sciences is definitely a core idea under physics. But the energy conservation and the fact that you have to think about that in any system you're looking at is a cross-cutting concept. What that means is students are asked to connect their ideas about energy that they learn in physics with ideas about energy in chemistry, in biology, in ecosystems, in earth systems. And at the moment, if you walked into those classrooms and when they were talking about energy, as a physicist you would know they were all talking about energy in some way, but you would notice that there's very little connection between the way you talk about energy in the physics class and the way a chemist talks about energy or the way a biologist talks about energy, which is often, for example, to say food is a source of energy, which doesn't make any sense at all when you think about it from a physics point of view. It's actually food plus oxygen allows a chemical process which releases energy, but food by itself is a source of nothing. So food is matter, and matter is something one needs to create energy sometimes or to release energy sometimes. So putting together the words in a way that works across disciplines was part of the effort of writing the framework, and it will be part of the effort of teacher education to make sure that teachers across disciplines talk to one another and think about, when I'm teaching about energy, how do I connect to the teaching about energy that went on in other classrooms? So that's one of the reasons for making these things cross-cutting concepts. I could go on in the same way about any one of these, and you can see how they work. I will talk about scale for a moment, because proportion and quantity and scale bring numerical measurement into things, but they also bring in a question. When you're asking about a system and you're asking what are the parts of the system, you actually have to ask the question, well, on what scale am I looking at the system? And then you have to say, well, for the problem of interest here, at what scale do I need to look at the system? So there are questions that link these cross-cutting ideas to one another. If I'm asking for example, how does a bicycle work, I work on the scale of wheels and cogs and gears and pedals. If I'm asking how do I build a lighter bicycle, I have to work on the scale of materials science and what makes lighter, stronger materials, which is at the atomic and molecular level. So different problems require different scales, and that should also be a repeating message that students get as they work across subjects and topics in their courses. So I see the practices and the cross-cutting concepts as the connective tissue that makes science science. What is similar about physics and what is similar and biology, well, it's that they both are concerned with these same cross-cutting concepts, and they both are concerned with the same set of practices, even as they focus in on different specific questions and disciplinary ideas. Noah, should you Do you have other
Wonderful.
questions?
Yeah, so we have some specific questions coming in that I think I might hold until the end, but this actually speaks to some questions that had come in. Michelle Benoit, apologies if that's not the pronunciation of your name, from Bangor High School suggested it would be helpful to have specific examples of ways to integrate with current curriculum with the new framework, to think about ways of segueing. And I think we're starting to get at that by recognizing and delineating key concepts that are going on. And that very much fits also with Julia Jenkins from Boston University's question about how do we best alter the curriculum and classroom activities to be at the forefront of the new standards in our public high schools and otherwise. And finally, I note that you talk about scales and the system across scales. Gail Brown keeps in mind, of course, that middle school is a key role here in this and actually may provide a unique lever for us in addressing science education, certainly bridging. So I don't know if you want to comment on those or if those examples are mechanisms that we can use.
I think this is a great place to comment on those. I mean, first of all, I think both the practices and the cross-cutting concepts can be introduced in whatever curriculum you're using right now, right? Just beginning to use the language of the way we've broken it up here and to expressly talk about argument from evidence or developing explanations, expressly talk about systems and system models. Each of those pieces of sort of global thinking can be introduced, because they are cross-cutting, they can be introduced in the context of any curriculum and any topic that you're working with your students with right now. I think the challenge is, of course, to ensure that as teachers are prepared to teach, they have a good understanding of all of these things. The 7 cross-cutting concepts and the 8 practices need to become key pieces of what teachers are aware of as they walk into the classroom, so that they can decide when to foreground a particular concept or a particular practice and when to focus on a specific system and particular piece of information about that system. So the shift can happen in any classroom for any teacher who's ready to take it on starting tomorrow for these things. The shift in assessments of these things, I think, will take a little longer to come.
Wonderful. Yes, I think this is, and we have some good questions coming in, but I also think that they are addressed in part by your subsequent slides. So let's return to those.
Okay, well, let's move on a little bit and talk about, because I think everybody wants to see and hear about the disciplinary core ideas too. I'm going to go fairly quickly through that because I think there's less that's novel here, except in the way it's organized. I'm sure you'll recognize things that you teach within these topics. And the first, whoops, I had a slide here about energy, but I talked about that, so we don't need to see that slide. In order to try and say what is a core idea, we gave ourselves some criteria because we were really trying hard, whether we succeeded or not, you can make your own judgments, to in some sense narrow the curriculum, to focus the curriculum on a set of core ideas so that we could get away from the lots and lots of details and no depth approach to teaching science. And so we gave ourselves these criteria. The first 2 are more or less the disciplinary criteria. It's an important idea in its discipline, and it's a tool for investigating ideas and solving problems. The second 2 are more about K-12 education, that this idea is something that's important for all students to learn, means it should in some way be important in the students' lives or be able to be connected to them. And that may foreground an idea which, when you look at it just from a disciplinary perspective, is not as core as it would be when you look at it from the perspective of what's important for students to learn. And finally, the last criterion is really to say core ideas are things that are big enough that they really develop across multiple years of education at increasing levels of depth and sophistication. So that was our attempt to guide our thinking as to how to choose and organize core ideas. And then I'm really going to give you a very quick brush across the top level of the core ideas. The framework itself goes into much more detail, and of course you can download and read the document if you want all that detail. So here's the physical sciences, and physical sciences includes, I would say, because this is what every student should learn, it includes perhaps a little less than our current physics course plus chemistry course, but it includes substantially more than, say, a standard 8th grade physical science course, or even 9th grade physical science courses that are taught in some places. You also see matter and its interactions, of course, contains the chemistry. It contains also some nuclear science, motion and stability, forces and interactions. That's the standard introductory physics ideas. Energy is defining energy and thinking about how energy is transferred and all the things you need to know about energy in order to understand what energy is. Number 4 is the stranger. In general, light and sound are taught as forms of energy. And because of the fact that light and sound also carry information, and therefore for us in our lives, they're very important. They're how we communicate with one another and with the world around us, both naturally and through all kinds of modern technologies. We decided that they were worth a separate topic just to make sure that that part of the role of light and sound in our lives was stressed, as well as the fact that they carry energy from place to place. So you see it's a slightly different organization than you would get if you were just looking at it from the point of view of what are the topics in physics. But then the same message carries on. So I'll go down the other subject areas. Here's the life sciences, nothing surprising. We start with organisms, and of course you have to look at organisms at the molecular scale as well as at the organism scale. We go to ecosystems, hereditary inheritance, variation of traits. That's the biology of variation, and that's separated out from the biology of evolution, which is the last topic. The order is not an order of importance. Some biologists wanted us to put evolution first as being the most important. The order is more so when we were writing our document, we could build the knowledge across these subject areas. Of course, for the students, they build the knowledge in all of these subject areas over time, so there's not an order as to when you don't do organisms first and ecosystems second as you go through elementary school. You do something that relates to each one of these core ideas and begins to develop it. Although the ideas about evolution start to develop a little later because you have to have built some ideas from the first 3 before you can start to think about evolution. So that's just an example from the life sciences. Then the earth and space sciences. Obviously the first one is space, the second one is earth, and it's a big one. The third one is, again, relating to the concerns of the students. Earth and human activity includes both the things that are usually taught in elementary school about natural hazards and how the earth affects us, and includes things like what human impacts on the earth, on biodiversity, and on climate change. So those things are put in here. And also actually in the life sciences under evolution, there's biodiversity and humans as a subtopic. So putting these things in to make sure that the connections to students' lives are brought to the surface, as again made explicit here, wouldn't be made explicit if you were just asking what are the core ideas of the science, of earth science. Finally, there's this fourth area, which is a little bit different and new. When you ask scientists to define what are the core ideas in their disciplines, they don't generally get to applications. But applications of science, and here I mean things like medicine, agriculture, technology, engineering, all across the disciplines, of course, are quite important in the lives of students. And making those links between the science and their applications and the impacts of the technology and the science on society is important for students at all levels. So we broke that out as a separate concept. The engineering design concept, you may have noticed there's engineering design in the practices. Why is it also here as a concept? Because it's both a practice and there is some knowledge that you need in order to engage in that practice, and that knowledge is what's incorporated in this subtopic under engineering design. This is by no means all of engineering. It's just a little piece of engineering thinking that one needs in order to engage effectively in engineering design. And where that gets fitted into the curriculum at the high school level, for example, is going to be one of those issues for discussion at the school level. It may be in career and tech ed courses. It may be in physics courses. It may be in both. So figuring out at the level of a local school system how the system ensures that students get access to all of the knowledge that this framework suggests and that the standards will ask that they have learned is an important step, which is not included in the work in this framework and still remains to be done across the systems. Finally, to stress again, in teaching, lessons should be three-dimensional. When we're exploring ecosystems, we're talking about energy and matter flow. We're talking about a system and a model for a system. We're applying the practices of arguing from evidence. So no matter what subject matter we're dealing with under a disciplinary core idea, it should be connected to the rest of science through the practices and the cross-cutting ideas. And that means that students engage in those practices. So, of course, from the point of view of teacher professional development, the question is how and where do teachers learn to do this? This needs to be very much part of practice and the understanding of the teacher about how you think about teaching content, that it's not just about teaching a particular disciplinary idea, it's also about engaging the student in doing things and in making connections to other ideas. So, as we said before, all these pieces have to be aligned, and that's a lot of work. I hope there are people on this webinar who are thinking about undertaking some of the pieces of this work, particularly those that have to do with teacher preparation, and I hope teacher professional development, because in-service teachers are going to need a lot of assistance in incorporating this way of looking at science into the way they think about their teaching. So there's a recent PCAST report that talks about revising undergraduate science. If you're talking about, let's talk about an elementary teacher. That elementary teacher probably takes one general science course at the college level, maybe not more. So that means that the introductory science courses at the college level need to have this model of three-dimensionality and have the teachers experience, have their students experience some level of these practices. Because if the students haven't, if the teachers have not met the practices, how can they teach them effectively? So often today, some of these practices don't really appear until you're in graduate school in science, unfortunately. And the claim here is they're important for every student at every level. And I think actually if one thinks about this model for the introductory science courses at the college level, it's as good a model there as it is at the K-12 level. that's me speaking, not the framework, but I believe that there's things to be learned about thinking about how you teach science at the college level here. And then, of course, if you're taking education courses on science teaching methods, are those courses aligned to this vision of what it means to teach science? Well, as systems try to align their practices to this vision of teaching science, it would help if the teachers coming into their system have their science methods courses aligned to that vision. So this framework puts demands that go well beyond change in the high school classroom to change from kindergarten through college level all the way to graduate level teacher preparation courses. And I'm just throwing it out there and then doing everything I can to make sure everybody who needs to be aware of it is aware of it, so that we can together make progress on all these fronts. Okay, Noah, over to you.
Wonderful. And I might suggest you hit to the last slide so people can see referenced. Thank you so much, Helen. This is really valuable for discussion. There's been lots of great questions coming in. So we'll move to those sort of two strands that we'll hit initially, and then please continue to send in questions. One is implications at the undergraduate level. Echoing your last statement, Jacqueline Spears writes, I'm concerned with the extent to which undergraduate STEM education is out of step with the expectations for what teachers should teach and students should learn. And at the same time, considering the broad span of undergraduate education, Margaret Fifield at Portland State writes, how can universities and community colleges frame the support for this? In particular, how can community colleges and universities act in concert to avoid crossed purposes or confusing or failed results in that? And is there a particular role then for curriculum coordinators to help teachers learn about the practices? And I suspect that this may well be a professional development role that might be held at universities or institutions of higher education. So perhaps you can
what is happening with the Mathematics Common Core is the beginning of development of alliances, regional alliances, which involve schools, community colleges, and colleges talking, universities, talking about who can best do which part of the work to support the transitions that are needing to take place. And figuring out, maybe there's capability at each of the levels. So professional development, yes, it's the responsibility of the school systems, but the school systems can work with university level or community college level people to provide both the reinforcement of content knowledge and the understanding of the different perspective on how you're teaching that is required to be fully three-dimensional. So I might also, there's a lot of room for alliances to be built, and I hope that work will be beginning. And as you point out in math, it has a strong complement to the Association of Public and Land-Grant Universities. Through their Science and Math Teacher Imperative, they've created this Math Teacher Education Partnership. There is talk about doing such a thing around science, and folks on this call may well, and perhaps through the American Physical Society, may be interested in helping build such a coalition as there become the next generation science standards. Yeah, I think we will need coalitions to do the work, and we will need lots of people both volunteering and I hope finding some ways to fund some of this work. I mean, that's one of the challenges right now. Of course, everybody knows that money is tight, whether we're talking at the federal level or at the local level. And school districts are already struggling with the burden of change that the Common Core is bringing. So throwing next generation science standards at them and saying, and this too, is challenging. And it's going to take goodwill on many sides, and I hope some federal investment eventually, but who knows when that will be forthcoming, to make this work. But I think certainly forming partnerships so we're not all working at cross purposes and we're working coherently and consistently with one another is a good place to start.
So following on, there was another theme, but very related to this. What are the international impacts, do you believe, from this? And folks wrote in earlier asking, how does this draw from or contribute to international efforts, whether in the European educational systems or from the Asian systems that are now investing?
So we did do some looking, and actually Achieve did a study for us that pulled together a review of what the curricula look like internationally. And the answer is they look different, different places. The one thing you can say is probably the common feature of the curricula in countries where students do somewhat better is they're more coherent. They have this idea of developing ideas over multiple years rather than just teaching whatever the subject is of this year. And so that, I think, is one of the pieces that we took very seriously in developing the framework. As far as the impact of the framework, I know it's being read all around the world. Again, as I said, you can take the practices and the cross-cutting ideas and meld them with any curriculum you might like to be teaching. And so I know that there are people, I'm in fact just off to Ecuador next week to talk about this in Ecuador. So I know that around the world there's interest and people trying to think, what does this tell us that we didn't already think about, or what should we be doing differently? It's interesting because both for science teachers and for scientists, I see a fair bit of resonance to these practices and cross-cutting ideas. People say, oh yes, I know what that means. But it's formulating it in a way that's expressible and communicable and shareable is the powerful piece, I think, of the document. And that then helps get a language which I think will start to affect international assessments eventually, but we will see. As far as
that's wonderful, yeah. I was going to move on to it.
I think the framework, that's part of the benefit of dividing the work in two steps. If you had standards, everybody internationally is going to look and say, well, those are just the U.S. standards. We don't take U.S. standards for our system, right? But if you have a framework and then standards, the framework is just expressing a set of ideas, and people can pick up which pieces of those ideas seem appropriate to them, and I think that is what is happening.
Wonderful. So I've got three sort of additional questions is now about sort of both breaking models, but then also the traditional boundaries that exist. So a question came in asking if there was any talk about reorganizing the order or even the traditional demarcation among the traditional courses. So to separate, no longer maybe separate biology, chemistry, physics, and environmental science. So that's
this is not a decision the framework made. The framework is very explicit, saying we are not describing courses. We are not saying you teach physical science one year and life science the next year and earth and space science the next year. We are saying this is the content that every student should meet no matter what sequence of courses they're taking. And then thinking about how best to organize high school, I think, is a whole nother piece of work. Actually, it's a very large and important piece of work. And organizing high school, once you start thinking about how best to organize high school science, you get into how best to organize high school even more broadly. And I think there's lots of different models out there, lots of different ways one could go, and every system will have to address that. Because if you just go the standard biology, chemistry, physics sequence, you won't meet some of the pieces here unless those pieces are carefully assigned into the pieces of that sequence. And there's also true that some states only require 2 years of science. Others, I think there's one state, Georgia, that requires 4. So it's a question of how can you can you? I actually doubt that you can reasonably cover all of what's in this framework in 2 years of high school science. I mean, all of what's in this framework at the high school level. Although I do think if you've got the middle school level, and this is a question I missed before, there's a lot here at the middle school level. And if the middle school is doing a good job of what's here at the middle school level, it will certainly put students in a better place to enter high school science with some tools ready to go. So I think the change will be iterative, because as the students entering high school have been through more years of experiencing instruction that incorporates the practices and the cross-cutting ideas, for example, then they will arrive at high school with a different set of tools than they arrive at high school with today. And so that also will mean ongoing change at the high school level, one hopes.
Wonderful. Yes. So since we're coming up at time, I'm going to first off is thank you very, very deeply, Helen. It's been wonderful here. I've had lots of good discussions with folks online. Crystal Bailey of the American Physical Society is going to sort of continue here and make some announcements, and we'll continue with some questions with you since you've graciously agreed to stay online here for a moment. So I'm going to forward some questions to Crystal, but Crystal will make some announcements here, and then we'll continue for a few minutes following that.
Yes, thank you so much, Noah. And it's great questions coming in. We're very excited that there's so much activity from the audience. I just want to make one or two quick announcements, and then we'll continue on. So for those of you who are leaving, I just want to remind you that you can also follow up. You can email your questions to webinars@aps.org, and I can forward those on to our speakers for comment. The slides of the presentation will be available on the main page for today's webinar, which you should be directed to after the broadcast. A recording of today's webinar will appear on this same webinar main page, but again, please allow 24 hours for us to upload that. And you'll receive an email from GoToWebinars within the next day or so containing the link to the uploaded video. And lastly, if you are leaving, in order to help us continue to develop quality webinar presentations, please take a moment and fill out the short survey when you exit. Okay, and that wraps it up for me. We hope you'll join us next time. Noah, I will turn it back over to you and Helen for continued discussion.
Okay, and I see Noah has already posted a question in the chat box about mathematics.
Yes, exactly. Especially in light of the Common Core state standards in mathematics, why isn't math integration one of the major themes in these standards?
Actually, if you look at the practices, you notice there's a practice called using mathematics and computational thinking. There's also a practice called obtaining, evaluating, and communicating information. And it's very interesting. If you put the practices from the Math Common Core, the practices from the science here, and something in the language arts called the student portraits, you find a common ground in the middle, which is about argument from evidence, and you find significant overlap between math practices and these science practices here. So it's not that the math is missing. It's not expressed in great detail in the top level description of the content, but it's very clearly part of the thinking that applying math at the appropriate grade level, math to science, is part of what one would want to see is happening here. So as this, again, that's part of turning it into curriculum and melding, particularly at the elementary school level, melding the science curriculum and the math curriculum in productive ways is certainly something that needs to be done.
Wonderful. And I think actually we're in a good position to be doing that, especially in light of your prior comments about building coalitions. I think as we build coalitions to enact these and support these, so too should we reach out, both learn from what the math community has done, but also then draw, coordinate.
And the other thing is the reading piece. I mean, science teachers today are being asked to teach reading. I think actually there's a slight misinterpretation of what that means. Obviously, reading in science is different from reading in any other subject. For one reason, one thing, you have to coordinate. You have to coordinate diagrams, graphs, equations even, with text. And that's not something you're going to learn to do from your language arts teacher. So there are aspects of reading science material which is just very different from reading non-science material and which need to be learned. The other part of reading in science is, of course, there's specialized vocabulary and language usage in science, and having students aware of and familiar with the way science uses language is important in order for them to be able to understand science texts. So there are aspects of not just the textbook, but of the way science is written, whether you're reading Science magazine or you're reading about science in a newspaper, that's just different from the way other subjects are written. And science teachers need to facilitate the students in being able to obtain information through reading as well as through other modes of interacting with information. The piece I also like to stress in the obtain, evaluate, and communicate is the evaluate. Information today is cheap. You just go online and you type into Google or whatever browser you like to have, whatever search engine you like to use, and you get tons of information on whatever topic you want. What you need is the ability to figure out what of it is good information and what of it is just junk or craziness. And that is something I think science teachers need to spend a little time thinking about and working with students about, so they have ways of looking at the information they're getting from the web to decide, is this or is this not a valid scientific source for information about this scientific topic.
And once we figure out how to support teachers in doing this, next are the politicians.
So, right. Well, that's another problem. I mean,
right, we don't need to go
here
there.
I speak as Helen Quinn and not as the framework committee, but it's my opinion that if students have had more experience in argument from evidence and evaluating explanations and developing things based on evidence, they'll be less likely to take statements at face value.
Wonderful. Absolutely. I think it's good for society writ large. So I think we're going to take one last question here and wrap up with that, which is there was a question asked, will there be science lab workshops? And I'm not sure if this is particularly about laboratory, but will there be workshops aligned to the standards to assist in-service teachers on a national level? And I might actually expand that to say science educators as well on a national level. Do you know if there are plans moving in that direction?
I don't know. I think there are organizations such as APLU, the Association of Public and Land-Grant Universities, who are thinking about the teacher preparation implications. And I think the teacher in-service implications become clear as you think about shifts in teacher preparation. But organizing, so teacher professional development is generally organized at the district level and then by professional organizations. So AAPT, NSTA, organizations such as that are the places where a lot of teacher professional development happens for the teachers who are in the know about how to develop themselves professionally. And certainly, I mean, if you look at the most recent NSTA meeting, the framework was a theme throughout that and being prepared for the next generation standards. So I think it will become more and more part of the conversation of whoever's doing professional development. Or at least they'll say they're doing aligned professional development, and then you're going to have to be a wise buyer to decide whether they are or they aren't. But I think it will influence all the places, informal science organizations like science museums who do work with teachers definitely are looking at this document and thinking about what does that say for their programs. So it's not that there's a national top-down organization of somebody saying, okay, here's where you go for professional development for the next generation standards. But I think there is a movement of change in professional development based on this document.
Wonderful. I will actually ask, because it's one, I think it's a yes-no question, and I think the answer is yes, which is to say, How set is the language on the science and engineering practices, cross-cutting concepts, and disciplinary core ideas in the report? The report is finalized. Is that correct?
Right.
This
is the report. It's out. The committee is no longer there. What is still open, of course, is the language in the standards. Those are being written, and when they go out for public draft, I hope all of you will make sure you get to look at them and comment on them and make sure that if there are places where you think we didn't get the language quite right, that it gets corrected there, because they are very closely basing them on our language. But I have said to the people at Achieve, look, we were not writing standards. We were writing sort of a top-level approach to the topic, and sometimes for standards you're going to need somewhat different language. We didn't have the time to do all the work that one needs to do to really get the language precisely right for standards, and that's why there are things in here where occasionally you look at them and you say, no, I wouldn't have said it that way. And I find those myself, even though I was involved in the level of this, writing of this all the way through. Every now and again I look at it and say, I wouldn't have said that this way. But
well, Helen, we appreciate your tremendous effort on chairing this committee, the establishment of these frameworks, which are leading to large-scale change. Your presentation here is tremendous, very valuable for all of us. Everybody who's participated, thank you so much. Do take Helen's suggestion to respond to the frameworks. Achieve is looking for public comment. They will have a short window, but they do take people's comments seriously. This will be posted publicly.
It will come out sometime. Will come out sometime in May, and there'll be a 3-week window to respond. So you're going to have to go to Achieve, ask to be put on their notification list, so that when it comes out, you can go to the achieve.org website and ask to be put on the notification list. And then when the drafts come out, you'll get them and you can go through them in as much detail as you have time to. I know it's not easy at the end of the school year for people who are teaching to find time to do anything but finish up their school year, but this is the timing that's happening, so it's your chance. There will be a second chance later, but of course earlier is better.
Absolutely. Well, and thanks to everybody for making this the most successful APS webinar to date. I'll turn it over to Crystal.
Yeah, I just want to echo what Noah said. Thank you, Helen and Noah, both for fostering a great conversation, and to all of our participants for also fostering a great conversation. And yeah, we hope that this was very helpful to you, and everyone have a wonderful day. I guess we'll sign off.
Don't forget the survey at the end.
Yes, please fill out the survey. All right.
Goodbye, everybody.
Bye.